Hi there, and welcome to our DLogs Honors Project final demo. Just as a quick recap, our overall project goal was to experimentally evaluate and compare different deep learning network traffic packet classifiers for the purpose of QoS and traffic engineering in community networks using the data collected from the OceanView community network. And the first project stage involved pre-processing the raw PCAPs into training, validation, and test CSV files, and the details of the stage were covered in the first demo. The second stage has then involved conducting individual experiments for our respective models, and we will now each present our findings.
In my section, I'll compare the MLP, LSTM, and SVM. For each deep learning architecture, the number of parameters were varied from 15,000 to 1 million parameters. The test accuracy and the number of packets classified per second was calculated at each parameter level. This figure shows the test accuracy for each model architecture. The points in this figure represent the different parameter levels. The SVM has a constant number of parameters with 14,800 parameters represented by the green dot. It can be seen that the deep learning architecture significantly outperformed the SVM model. Also, the LSTM reaches a much higher accuracy than the MLP for all parameter levels. It can be also seen that in general, as the number of parameters increase, the accuracy increases at a decreasing rate. This shows that the number of packets classified per second by the LSTM and the MLP over the different parameter levels. There is some noise in the data, but this proves that the MLP has a faster prediction speed when compared with the LSTM. The time taken to make a prediction was calculated for only a single sample. This figure shows that if you classify multiple packets at the same time, you can create faster prediction speeds. It also shows that the MLP is faster than the LSTM across all batch sizes.
For my section, I'm going to be analyzing the performance of the 1D CNN for the network traffic classification task. To do this, I built deep learning and SVM models across 4 different input sizes with different architectures for the deep learning models. These models were compared across their performance between each other, as well as within each other for the trade-off between prediction rate and accuracy. Finally, the best model out of the set of all models that could meet the different community network resource constraints was selected for each network constraint. This graph shows that the CNN attains the highest accuracy on the full input length out of all of the models. MLP second highest, and SVM is lower than them. We can see that the full input length performs better than truncating input length. The MLP is significantly faster than the CNN, and the SVM is much faster than either of these models, and hasn't been included on the graph here because it's used the scale too much. You can see here that there's a negative trend between test accuracy and prediction rate for the MLP, so high accuracy is slower. Same with CNN with the L shape here. And for the eventual model allocations, the SVM was given to the weakest network, MLPs to the mid-range one, and only the fastest network could support the CNN.
In my section, I evaluate the suitability of 2D CNNs to the community network traffic classification task. This is done through 2 experiments. Experiment 1 compares the accuracy and prediction speed for 5 models against number of parameters chosen on a log scale. The models considered are shallow and deep 2D CNNs, shallow and deep MLPs, and an SVM model. Experiment 2 evaluates the effect that reducing the number of packet bytes used as input has on the deep CNN's accuracy and prediction speed. This figure shows that the deep CNN significantly outperforms the other models on the basis of accuracy, and that the neural networks outperform the simple SVM given sufficient model complexity. The benefits of deep learning are demonstrated by the better performance across the parameter levels offered by the deep CNNs and MLPs compared to the shallow CNNs and MLPs respectively. We also note that the general trend for the models is that the accuracy increases as the number of parameters increase, but at a decreasing rate. This plot clearly shows that the smaller the model, the faster the prediction speed. We observe that the MLP models have a significantly faster prediction speed than the CNN models at all parameter levels. Additionally, the SVM model was more than 5 times faster than the fastest MLP model, demonstrating its advantage in terms of speed. Finally, this figure shows how the deep CNN model's prediction speed improves significantly as the size of the input decreases. Whilst this does come at the cost of a decrease in accuracy, the accuracy levels are still high relative to the baseline MLP and SVM models.